So today we're going to be looking at a few more verifying trig identities. So again, like yesterday, what we are doing is we are saying that these are true, that these are true statements here. We are just going through and trying to prove why exactly they're true. So remember, to do that, we pick one side and we can only concentrate on that one side as we're going through it there. And then we need to kind of go through our identities and prove that it does in fact equal the other side. As I was looking through some of the homework that people were turning in, I did see a few people kind of skipping through steps. I know it's really tempting to want to skip through steps, but really the whole idea behind this is really visualizing and showing that proof. So you do want to show all of your steps here. So I'm going to go through one of these here. I'm going to actually go through it probably in two different ways, just to kind of show you that there are other options. The answer keys that I show aren't always exactly going to be how you do it every single time, but it should still give you the same results. So on this one, I'm going to start on doing our left side. Then the second way I'll go through is how we can do it, verifying from the right hand side. So if I look at the left hand side, I've got the cosine of theta over 1 plus the sine of theta. So that's on our left-hand side. Again, that's equal to whatever we're saying, it's equal to whatever's on the right-hand side. Excuse me. So when I look at this, I can see, all right, I have two different trig functions that aren't related to the ones on the left-hand side here. So I need to somehow think, how are we going to turn it into two things that are being subtracted? So when I look at the left-hand side, though, I see that we've got a cosine and a sine. Right now, there's no way that we can really change that into the other. So what I want to think about is, how can I make these squared here? Because if I have it as a cosine squared or a sine squared, I can change one into the other. Now, be careful on this. I sometimes find people wanting to try to square both sides. You're not allowed to do that when you're going through and verifying the identities. It's not an equation that we're solving. We actually can only deal with the one side. So instead of squaring both sides, what I can do, I'm going to look at that denominator and I see a 1 plus the sine of theta. What I can do is I can multiply that by 1 minus the sine of theta. If you remember at all from last year in Algebra 2, you talked about things called the conjugate. You probably did this when you were dealing with imaginary numbers or complex numbers, what we call them. If this is 1 plus the sine of theta, if you multiply by 1 minus the sine of theta, it actually does something useful for us here. Now, again, as long as you do it, you have to multiply the numerator and denominator, because really what you're doing is multiplying by the equivalent of 1, so you're not changing anything on the left-hand side. So I'm going to leave the numerator right now as the cosine times 1 minus the sine. Now, you could multiply it out. I see two different functions, a cosine and a sine, so I'm going to leave it for right now. Sometimes it's helpful to multiply it, sometimes it's not. Sometimes I tend to wait to multiply it until later if I determine that I want to or not. So I'm going to wait on this one. But in my denominator, what I can think about, since we have just both signs here, I am going to multiply it out, because that's really the whole reason of multiplying by the conjugate. Because if one's a plus and one's a minus, the middle term cancels out. We get 1 and then minus sine plus sine and minus sine squared. So it's really 1 minus the sine squared. So now 1 minus the sine squared is the cosine squared. So now that got rid of a little bit in that denominator here. And now that we really only have one thing in the denominator, that might be helpful to kind of go through and think about a little bit. So if I look here, I've got a cosine in the numerator, cosine squared in the denominator. One of those can cancel, so that means I get a 1 minus the sine of theta over the cosine of theta. Again, I always like to kind of go back to what I'm looking at. I need a secant and minus a tangent here. So I do need to separate them. I want it to be, a subtraction problem instead of a fraction. Now that I have the one thing in the denominator, I can separate it a little bit easier. Now I can write it as 1 over the cosine minus the sine over the cosine, since they have that same denominator. And conveniently, if you go that next step, 1 over the cosine is the secant, and the sine over the cosine is the tangent. And if we go back up and look, that's exactly what we wanted to prove. we just verified it. I sometimes like to put a little check mark like, all right, we verified it, we're done, we got that one. Again, that's not the only way to do this problem. There's a lot of times different ways to do it. Let me just kind of go down here. You could have tackled it from the right-hand side as well. Now, do I need you to do both? Absolutely not. This is a second option for you. I'll put a big, oh, whoa, sorry. I'll put a big or on this here. Again, you don't want to do both on here. You want to just think about choosing one of them. All right, so if I do it looking at our, sorry, right-hand side here. So I'm going to look at it over here. So let's start with, all right, we have it equal to the secant and minus the tangent here. Okay, so I'm going to start with this. So if I'm looking at the right-hand side, comparing it to the left-hand side, clearly we need to change things in terms of sine and cosine because the left-hand side is only sine and cosine. So that's easy to do with these. We know the secant is 1 over the cosine. We know the tangent is the sine over the cosine. And again, if we look on our left-hand side, we see we want it as a fraction, so we're going to want to actually subtract them. Conveniently, we already have a common denominator, so I can do that. Okay. Now, you have a couple options on this one here. Now, you could kind of do what we did in our last one as well. I could multiply the numerator and denominator by 1 plus the sine of theta and go through it that way. I could multiply the numerator and denominator by the cosine over the cosine. I could have done that on the left-hand side as well. And gone through it a different option as well. Again, there's a lot of times different things that you could do. Just to be a little bit different on this one, I'm going to multiply numerator and denominator by the cosine. Again, you could absolutely also multiply numerator and denominator by 1 plus the sine of theta. That's actually a pretty easy way to go through it as well. But just to show you something a little bit different, because what that does for us here is that gives us the cosine squared in our denominator. And in our numerator here, we have the cosine times 1 minus the sine here. So again, I just wanted to show a different option for you here. If I'm looking at this here, our goal is to get a 1 plus the sine of theta in that denominator. So that means I'm going to change the denominator into sine. We know cosine squared is 1 minus sine squared. I'm going to leave this here. And now that I have that denominator we know is a difference of 2 perfect squares. So I can factor that. So that factors to, 1 plus the sine of theta and 1 minus the sine of theta. And then the 1 minus sine of theta can cancel, and we get the cosine, oh my goodness, over 1 plus the sine, and that's exactly what we wanted. It won't let me write there. So that's exactly what we wanted. Again, there are other ways to do this. You could have, like I said, multiplied that numerator and denominator by 1 plus the sine of theta. That way actually might have even been quicker, less work, but I just wanted to show you that really there's a couple different ways that we can go about doing these. So that's another option, or another example, I should say, for verifying identities. So I want you to look at number 2 and number 3. Number 2, there's again a couple different ways to go about it. You probably want to tackle the left-hand side since that's more complicated. But again, there's actually a couple options. You can change things into sine and cosine and work from there. You can look at that denominator and do something similar to what I did on the left-hand side. There is one way that's a little bit longer. There's one way that's a little bit shorter. I'm not going to tell you which is which. Just kind of play with it. It's kind of like a puzzle. Number 3, again, same idea. You could tackle from one side or the other. The back side then is some review. I thought I'd go through just one of these just to refresh your memory on what we did before spring break. If you're looking at number 4, I'll go through that one. Here we only have one trig function. The sine of 2x is equal to that root 3 over 2. Since it's only one trig function, I'm not going to use any identities in this one because we can already say, all right, we know 2x has to equal wherever the sine is root 3 over 2. But you do have to be really careful with that interval. So our interval is between 0 and 2 pi. But that means if I'm looking at 2x is going to be between 0 and 4 pi. Again, if you multiply all of this by 2 in order to get that 2x in the middle, that's really what we're focusing on right there. So that means we still want to think, where is the sign root 3 over 2? Hopefully we didn't forget our unit circle here. So where's our y coordinate root 3 over 2? That'd be up here and over here. So that's at pi over 3 and 2 pi over 3. But we need to think about that interval. Both pi over 3 and 2 pi over 3 are both between 0 and 4 pi, so we're good. But that means we still need to go a little bit bigger here. So we need to find the coterminal angles. So I'm going to add 2 pi, which is 6 pi over 3 if we're doing common denominators. So if I add 2 pi to pi over 3, that gives us 7 pi over 3. And if I add it to 2 pi over 3, that gives us 8 pi over 3. If you wanted to keep going, test it. 6 pi or 7 pi over 3 plus 6 pi over 3 would give you 13 pi over 3. But again, 13 over 3, 13 thirds is the same thing as 4 and 1/3, right? That is bigger than 4 pi, so we're not going to use that one in there. So I'm going to cross that one off, erase it even. These are the four ones that we're going to be looking at, and we're going to divide everything by 2, same thing as multiplying everything by a half, and that gives us pi over 6. It gives us 2 pi over 6. I'm even just going to reduce that one right away to pi over 3. 7 pi over 6, and 8 pi over 6, which would reduce to 4 pi over 3. Okay, so that's a good review from problems like that. If I look at number 5, it's going to be similar, but we have to adjust our interval with the x plus 3 pi over 4. Number 6, notice, it's kind of hard to see, it's typed a little weird. There's a 2 in there, so you've got a couple things to think about. Now look at number 7. I'm not going to go through it all right now, but if I look at number 7, I've got a sine of 2x and a cosine of x. Again, there's two different functions in there. So we can't treat these the same as we did 4, 5, and 6 because there's two different functions. You can't say, all right, 2x is going to equal something because it's not equal to like our, root 3 over 2 or 1/2 or something. It's equal to the cosine. So on this one, I'll give you the hint. You may need to use some identities on this one here because, again, we don't want it in terms of two different functions. You may have to use some identities. You may have to think about some factoring or other ways that we use to solve those. So try them on your own, and we can talk about them the next day. Thanks. Bye, guys.